Of course, all rivers go to the sea. But do our command lines get executed? Do they flow linearly to the same place? Well, the answer is absolutely no. We will see that the flow of a program is much more complex, much more sophisticated, and in fact, in this complex flow of a program is the algorithm. The way we solve problems is not just by the commands, but also in their interrelations. Welcome to unit number 3, Program Flow. We will talk about conditionals, how we set the terms for each command to be executed or not. Then we will go to nesting, when we put one conditional inside another conditional. And the next chapters, the iterations, the range, and the loops, they are all around making the flow of a program go from down to up in an iterative manner, in a loop, if you will. And lastly, we will see some usage approaches. So let's begin with conditionals. So the flow of a very simple program is of course linear. We've written a few lines of code and they will be executed one after another in the order they were typed. However, the flow of most programs depends on the values of variables and relations among them. We will have variables and we will have values, of course, and they will help us determine how the program flows. For that, we need conditional statements. They help us direct this flow. Here is an example. We will use the command if to check whether 365 is fully divisible by 12. I mean, there's no remainder. For that, we will use the if command and also the modulo sign, the modulo operator with the percentage mark. So, if 365 modulo 12 equals 0, it means that the result of the modulo, which is the remainder, is 0. So, of course, it means that 12 divides 365 fully. If this is the case, we will print 365 is divisible by 12. Else, if not, if the remainder is more than 0, then we will print 365 is not divisible by 12. So here is the first way to direct the flow of a program. It's either the first print that will be executed or the second print that will be executed. In no way it will be both of them. What will be the result of this if we execute it? Of course, it will be 365 is not divisible by 12. That's why we have February. Okay, so what did we see here? We see the if command, it is in one line, and there the column. And after the column, we have a space, it's called indentation, and then the print command. Let's see it in a syntactic way. The syntax of the if command is that after the if statement, after the column, we open a new scope, like a new block. This block may contain one or more Python commands, Python statements, and they will be executed only if the condition in the if command is true. Now, these lines of code that are inside the scope, like the print statement, are indented to the right. This indentation indicates that the print command is inside the if command, is inside the if command's scope. And how do we mark the end of this scope? By losing the indentation. So the first statement that is not indented in this way, in our case it's the else, but we will see other options, is the mark that the scope has ended. It is outside the scope. For the indentation, you can use either tabs or spaces. Tabs is better. But what you need to know really is that the most important thing is consistency. So the width of the tab or the number of spaces must be consistent along the code, specifically along the scope of a certain if command. But we all want consistency all over. So it's better to be consistent along all the program. Many times it's not practical, and we will allow some inconsistency, for example, when we copy and paste codes from a different place. So the way we write the if command and the way we construct the scopes contributes to an important element in good programming, which is elegancy, as you can see here on the right. This methodology is actually very important. You'll be surprised, but the more elegant our code is, will not make it run better or faster or give better results, but the development process, currently done by humans only, will be much better. As you can see here, the flow of the program is very transparent. We can actually see the rationale and the hierarchy of the flow. If this, then that, else that. That's the beginning of an elegant structure. Do you want to see something that is not really so elegant? I'm kidding. If in doubt, you can always use help. So this is what you will see. The if statement is used for conditional execution. And then you can see what Python has to say about it. But as we said in the past, it's useful, but it's a bit cryptic. Next chapter, nesting. We will see how we can put one if command inside another if command, so-called to nest one command in another. In this case, we will calculate an n variable as 2 to the power of 97 plus 100. Now, if n modulo 4 is not 0, then open a scope that has several commands. First command, print n equals as a string and then n as a value. And then another command inside the scope, print n is not divisible by 4. Else, now we go into another scope. And in this scope, we begin with another if command. This is the second if command that is nested inside the first if command. Anyway, it checks whether n modulo 8 is not 0. If so, it prints n equals n, and then n is not divisible by 8. Else, and this else is also nested under the first if command, but it belongs to the second if command. That's the hierarchy, as we can see in the indentation. And in this case, we just print n equals n, and then n is divisible by 4, but not by 8. So you see now in a very elegant way, we can see the flow of the program and also the relations between mathematics and the specific algorithm we see here. Now, nesting is a very powerful tool, of course. It allows us to make all these complex structures and in many cases the sophistication of the algorithm. And therefore, we need to keep in mind the KISS methodology we talked about in the former lecture, which means keep it simple, stupid. Indeed, we want the hierarchy implemented by nesting to be simple and even more so, to represent logic. Then again, the connection between the syntax, the hierarchy, and the logic of the algorithm. More about that, much more about that, in the near future. Now let's take this syntax that we learn, this mechanism that we learn, to another cornerstone activity, cornerstone operation in programming and in general in problem solving, which is iteration. Iteration means the act of repeating a process, usually with the aim of approaching a desired goal or target or result. Each repetition of the process is also called an iteration, and the result of one iteration are used as the starting point of the next iteration. I did not invent this text, this definition. It is from Wikipedia, and it's true. Now let's see an example. It is very, very common that we want to iterate a portion of the program, possibly with different arguments. Here, we want to repeat the process of adding numbers. Something like what you see here, 1 plus 2 plus 3 until 10. We can, of course, write an expression like that and put it in the prompt. If we do that, we do get the results. But of course, this is only a simple situation that can be good enough if we just want to add the numbers between 1 and 10. But of course, what will happen when we wish to increase the summation limit to 100, 1,000 or 1,000,000? Of course, we will not want to do that, and we don't need to do that to manually write each and every number one by one. Right? It's repeatable. And here I want to mention another methodology, which is DRY, a short for don't repeat yourself. We don't want to repeat ourselves because it's tedious. Computers are good on repetitions, so why do we need to repeat ourselves? Moreover, when we repeat ourselves, we are more prone to errors, just because we are humans. So obviously, we ought to have a more efficient method to express such iterated addition. We want to iterate over the integers in a range between 1 and 100, 1 and 1,000, 1 and 1,000,000, or any range, and repeatedly to add the next element to a variable which is the partially computed sum. Let's see how we do that. We need two entities, range and loop. Let's begin with range. There's a syntax to define such ranges. It's a construct called range, which creates an ordered collection of all integers in a given range. For two integers, let's say a and b, range and then in parentheses a, b, this is an expression that contains all the integers, let's call them k, that are between a and b. And as you can see in this mathematics, the range contains a, but doesn't contain b. This is the syntax. So range 1, 10 will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and not 10. Note that if a is larger or equal to b, according to the syntax I just mentioned, the range is actually an empty list. But that's logical. So it's not an error. It's a range in the size of 0. Another syntactic method is to write just range, let's say b, which is a short for range 0b. All the numbers between 0 and b minus 1 included. So let's see, range 1, 90. This is an expression. This is a construct. So when we put it in the command prompt, we just get it back. This is the value of the expression. What is its type? Class range. Good. From this class, we just get an iterator. It's like a pointer to the first element in that range. And we can run this iterator over the range. So range returns an iterator that generates all the numbers in the range on demand. You can of course see help if you need more assistance. But let's move on to the next element, which is controlling how this range progresses. We can do that arithmetically. So for these three integers, a, b, and d, when d is more than 0, we write range a, b, d, And this range will contain all the integers from A till B in steps of D. We can say it's something like A plus ID. I stands for iterator, D is the step size, so I multiplied by D, as long this condition is satisfied, where A is smaller or equal to A plus ID, and also that A plus ID is smaller than B. This is the range that we want. And now if you think about it, when we just write range AB, it's like a short for range AB1. We can also have negative D. In many cases it is very useful or just required. And in the same mathematics or the same logic, it will go from a high number to a low number in a reverse order. So we can have either positive D or negative D. What we cannot have is D equals 0. It will be like a stuck range, right? Okay, so that was the first element that we need, which is the range. And now the second element that we need is loop. The loop is actually the element that makes the iterations, but it does so according to the range. Let's see. Suppose we want to compute 1 plus 2 plus 3 plus until 100. What will be the range for that? The range will be range 1 till 101, right? Because we don't get to the last number. So the last number will be, in this case, 100. This is what we want. But now we only have iterator that can scan this range. We didn't do the calculation. We didn't do the summation. In order to do that, we need to write some code. So here is how it goes. We have a new variable. We call it partial sum. It will store the partial sum step by step. We initialize it to be 0, of course. And now a loop command called for. This is one loop command. We will see soon another one. So for is a loop command, and the syntax goes like so. For I in range, whatever the range is, in this case 1, 101, open a new scope of commands. This is what we see with the column. Now I is the actual iterator, is a variable that will iterate over this range. And of course, because it's a variable, it can have any name. So in this case, we call it I, which is quite a common practice, I for iterator. And now what do we do in this scope? We take the partial sum variable, and inside it, we will put a value which equals the former partial sum plus I. That's it. So let's see how it goes. In the first iteration, partial sum is 0, of course. And now we begin the loop. So for I in range 1 to 101, I in this case will be, because it's the first iteration, will be equal to 1. So partial sum equals to, now we look at the expression to the right of the equal sign, calculate it first. So partial sum was 0, currently is still 0. We add to that I, which is 1. So partial sum plus I now equals 1. And this is what we put to the left, to the variable on the left, which is partial sum. So now partial sum equals 1. We reach the end of the scope of the loop, and therefore the interpreter, the little person inside the computer, will go back to the beginning of the scope, but this time I receives the next value in the range. So now I equals 2, going now inside the scope. Partial sum plus I now is 1 plus 2, which is 3, and 3 enters the variable on the left, which is partial sum, and now partial sum equals 3. And this is indeed the result of the second step of the iterative process. We are at the end of the second step, so we just completed 1 plus 2. In the next iteration, I will be 3, and inside the scope, partial sum, which was 3, will be added by I, which is 3, altogether 6, which will be entered to partial sum, and indeed 6 is the result after 3 steps, 1 plus 2 plus 3, and so on and so forth until we reach 100. The next command could be just to see what is the value of this expression, of this variable. So we just write partial sum, and what do you know? 5050. You can check. So, in conclusion, in this statement, for and in are reserved words in Python, causing this loop, causing this iterated execution of the addition command, or just whatever will be in the scope of the for command. But in any case, the variable I goes over all the elements in the range 1 to 100. Again, the colon and the indentation determine the scope where the iteration actually occurs. So the structure is, of course, very important. Now, this is how loop works, in this case for summation. However, just for summation in particular, we have like a built-in function. Its name is sum, and it's very good to use it. It makes our code more concise. So for example, if we want to do the 1 plus 2 plus 3 plus 100, we can just write sum, range, and then whatever the range is, 101. The result is the same. Now, if you remember, I said that for is only one command. Another command for loop is while, which is more freestyle. Let's see an example. Let's say we want to print all the divisors of n, for example, when it equals 100. So we say n equals 100, and now we will use another variable just to do the iterations. So our iterator will be m, and we begin again with 100. We will reduce this m to be 99, 98, 97, and so on. And the way we do that is as follows. So we say while m is bigger than 0, because 0 is the last point, then we open a scope. In the scope, we check whether m divises n, or in other words, if n modulo m equals 0, then we open another scope, which is nested, right? And in this case, we just print m, the divisor. The next step will be to reduce m by 1. And notice that this operation should not be inside the if. It should happen anyway in every step of the iteration, in every step of the loop, whether m divised n or not. And this is why the indentation is narrower. We went back to the hierarchy of the scope of the loop. That's it. The result is 150, and then 25, 20, 10. These are all the divisors of 100. It stopped at 1 because this loop is entered and executed as long as the condition in the while command, which is m is bigger than 0, holds. So in the last iteration, what happened really was that m, which was 1, now got reduced in the last command to 0, and then m equals 0. And then the little person inside the computer went back to the while command, the while line, and checked whether m is bigger than 0. The answer is, of course, no. So the loop is completed. If we fail to do this progression command, the m equals m minus 1, then m would not change. M will always be 100. M will always be bigger than 0. And this is where we go into the big problem of infinite loop, and it will get our program to stuck. We will see some examples of that later. You will see many of these examples when you do coding. But don't worry, you will get used to writing the perfect loops. We will now see a few usages, but first a historic, small, non-iterative digression. This gentleman is Carl Friedrich Gauss, who was only 6 years old when allegedly he figured out a way to efficiently calculate the sum of 1 to 100. What have you accomplished at the age of 6? Here is what he did. He understood that 1 plus 2 plus 3 plus n equals n multiplied by n plus 1 divided by 2. Of course. Now, it's not that we are going to use it. It's just for educational purposes. We will just simply let the computer chew its way through the iteration. It actually points out a very important factor in computer science, which is efficiency. It is also one of our methodologies to make efficient code. But anyway, what his observation was that the calculation now can be much faster. In modern terminology, we could say that his method, requiring only one addition, one multiplication, and one division, is much more computationally efficient than our method, our iterative method, that requires n minus 1 addition operations. Of course, if n is small, then it doesn't really matter. If n is large, which is the case in many other scenarios that we encounter in our modern lives, it does make a difference. Anyway, we will define these notions in precise manner in one of the next lectures. Let's just see it in action. We want the sum of the range of 1 with 8 zeros, 100 million. This should be that number. Now, for the computer to do so, it needed to do 100 million calculations. And this takes some time. However, if we do the Gauss way, as you can see here, only very few calculations, and the result is the same, of course. Gauss was right, and it is noticeably faster. And this is our lesson. Good algorithms often succeed to tackle problems in non-obvious ways, and by that dramatically improve their efficiency. This thinking how to do things efficiently is a core competence of good programmers. One of the reasons why I like this subject so much. Last thing I want to show you now is a small command called break. That breaks a loop. Let's go back to our loop for I in range 1 till 101. Just print I. But if I modulus 7 equals 0, so if I is divided by 7, then break. The break command will just break, will just stop the loop, and therefore the result will be 1, 2, and the rest 3, 4, 5, 6, 7, and then we break. We stop the loop command and continue with the next command, whatever it is. It terminates the nearest enclosing loop, skipping any other code that follows the break inside the loop, and of course the following iterations. It can occur in both for and while loops. It is useful when you need to, at some predefined condition, to get out of your loop, but it is considered bad programming. You better put whatever condition you have inside the conditional of the for loop of the for command line or the while command line, and not buried inside the scope. You will see real hands-on examples of that in the practice sessions. Enjoy it, and I will see you soon.